Concentration, temperature, and molecular weight dependent on optical properties of vinyl pyrrolidone, in chloroform solutions. Abstract: we report on the concentration, temperature, and molecular weight dependent of some optical properties of vinyl pyrrolidone. PVP dissolves in chloroform for different molecular weights, 25K, 44K, and 700K, at different concentrations, 0.1-10W/V%, with temperature range, 25 to 45 degrees Celsius. Refractive index has been measured to determine the optical parameters including, reflectance, coefficient of fineness and critical angle. The results show that refractive index, reflectance, and coefficient of fineness values increased with increasing concentration and molecular weight, whereas the temperature had a different influence. However, these parameters were decreased with increasing the temperature. On the other hand, critical angle values the results presented that the refractive index, reflectance, and coefficient of fineness of the polymer decreases with increasing the temperature while the critical angle has the revers behavior. Keywords: vinyl pyrrolidone, chloroform, polymer solutions, optical properties, refractive index, reflectance, coefficient of fineness, critical angle. Introduction. Polymers are currently attracting considerable research attention because of their broad industrial applications. Basic polymer features such as easy production, low initial cost, durability, and exceptional processability necessitate its use in several scientific applications. 1, 2. Polymers in many instances can also tolerate easier shaping and better processing of the composite materials. Vinyl pyrrolidone, PVP is one of the attractive polymers due to the strong affinity of the pyridine group and its ability to undergo the hydrogen bonding with polar species 3, 4. PVP does possess a unique combination of properties, such as environmental stability, with inert physicochemical properties over a broad range of pH values 5, good solubility in both water and a range of organic solvents, a remarkable capacity to interact with a wide variety of organic and inorganic compounds, good biocompatibility, compatibility and resistance, and non-toxicity to living tissues. For these reasons PVP has been widely used in the biomaterials and coatings, pharmacy, cosmetics, and industrial production, blood plasma substitute, which closely affect human health. 6. PVP has also been widely used as a medical additive or polymeric modifier. In fact, PVP is one of the most frequently investigated classes of materials for usage in medicine and in other applications interfacing with biological systems. 7 to 10. Another advantage is that PVP large-scale screen printing of PVP films at low cost is feasible, and it is also used in detergent formulations where its role is to prevent redeposition of soil on fibers. PVP can be thermally cross-linked, thus ensuring a good thermal stability and mechanical strength, and also because of the stability of PVP in water. 11, 12. It should be noted that the formation of the transition metal particles inside the polymer system is also of interest for some potential applications, including the storage of optical data, shielding of the electromagnetic radiations, as flexible elements for resistive heating, laser systems, optical lenses, and integrated waveguides, easy processing, and moderate electric conductivity for batteries and displays. 13 to 15. The interactions between water-soluble polymers and metal ions have a significant influence on the polymer physical properties. 16, 17. PVP thermally decomposes before reaching its molten state. This terminates the application of this polymer. PVP is chosen as a matrix for the composites because of the two important characteristics. 18. PVP has good film forming and adhesive behavior on many solid substrates, and its formed films exhibits good optical excellence, high transmission and visible range, and mechanical strength, easy dispensation, required for application. 7. The amorphous structure of PVP also provides a low scattering loss, which makes it as an ideal polymer for composite materials for different applications. PVP is easily soluble in water, so it is preferred to avoid phase separation in the reactions. 8, 9, 19. The PVP polymer film has a potential capacity to store the charges responding to the dopant-dependent electrical and optical properties. It has a strong tendency for complex formation with a variety of molecules. 10. In literature, alkali ions containing polymers are reported to be more promising, possessing potential applications. 20, 21. 2 experimental methods. 1 materials. The 3 molecular weights 25K, 44K, and 700K of PVP were obtained from BDH Limited, England, and were dried under vacuum at 60 degrees Celsius before use. Chloroform was of Riedel, DN, and Hanover product, monobromonaphthalene. 2 preparation of solutions. PVP 25K, 44K and 700K solutions with different weight per volume percentage of 25K and 44K, 0.1-10W/V%, and 700K with range, 0.1-5.0W/V%, G/ml have been prepared by dissolving the propagate weights of PVP 25K, 44K and 700K powder in a fixed volume, 100 ml, of chloroform by using magnetic stirrer in mixing process for 15 minutes to get homogeneous solutions. 3 refractive index measurements. The refractive index measurements were carried out using the refractometer type Kerzai/Germany. The temperatures of measured solutions were controlled within 0.5 degrees Celsius. The refractometer was checked by standard material monobromonaphthalene. 3 results in discussion. Refractive index has been measured for 10 different concentrations, 0.1 to 10%, of PVP in chloroform solution of the molecular weights, 25K and 44K, and for 7 concentrations, 0.1 to 5.0%, of PVP for the molecular weight 700K in chloroform solution. All solutions were measured at 5 different temperatures, 25 to 45 degrees Celsius, at 5 degrees Celsius intervals. The optical constants such as reflectance, coefficient of fineness and critical angle were calculated also for all above-mentioned concentrations at the same temperatures. The results of the analysis of obtained data were discussed by looking at the general behavior of the considered optical properties as a function of concentration, temperature, and molecular weight. 1. Refractive index, ND. Refractive index is one of the most important optical properties of a medium. It plays vital role in many areas of material science with special reference to thin film technology and fiber optics. Similarly, measurement of refractive index is widely used in analytical chemistry to determine the concentration of solutions. Refractive index is one of the most important optical properties of a medium. It plays vital role in many areas of material science with special reference to thin film technology and fiber optics. Similarly, measurement of refractive index is widely used in analytical chemistry to determine the concentration of solutions. Refractive index is one of the most important optical properties of a medium. It plays vital role in many areas of material science with special reference to thin film technology and fiber optics. Similarly, measurement of refractive index is widely used in analytical chemistry to determine the concentration of solutions. The refractive index is defined as the ratio between the speed of light, c, in a vacuum to the speed, v, of any center of a certain length and a certain wavelength, gives the following equation 22, 23. The refractive indices of all PVP solutions were measured at the same temperatures range mentioned above, and the values of at least 4 readings being averaged, for the 3 different molecular weights 25K, 44K, and 700K respectively. 1.1 Concentration Effect. To study the effect of the concentration on refractive index, ND, for each system of PVP in chloroform solutions was plotted against concentration for 3 systems in its selected temperature 350C, as an example. The refractive index linearly increasing with the increasing of PVP concentration as shown in figure 1. This behavior attribute to increase of the density with increase the concentration 24,25. For 3CO35I and chloroform solutions at of PVP refractive index dependence of figure 1 concentration different molecular weights. 3.2 Temperature effect. The variations of refractive indices with temperature are evaluated at 3.0% PVP. Figure 2 shows the refractive index as a function of temperature. It is clear that the refractive index of the polymer decreases with increasing temperature, and the results showed linear relationship between refractive index and temperature of the polymer within the ranges of temperature. This behavior is due to the temperature effect to activate of the kinetic atoms of the polymer, and this may be due to the fact that increasing temperature decreases the density of the solution 26. 1.3 Molecular weight effect. The refractive index dependence on the molecular weight of PVP in chloroform, for selected 3 concentrations, 0.3, 2.0, and 5.0%, and temperature 350C as an example, is demonstrated in figure 3. It can be seen that the increasing of molecular weight rather rapid increase in the refractive index of these solutions. This general increase of refractive index with molecular weight may be due to the increase of polar side groups in the molecular chain of the polymer 27. 2. Reflectance, R. When light radiation passes from one medium into another having a different index of refraction, some of the light is scattered at the interface between the two media even if both are transparent. The reflectance can be represented depending on the value of refractive index by using equation 2.24, which the reflectivity of PVP solutions was studied for concentrations and temperature of the 3 different molecular weights, 25K, 44K, and 700K, respectively. 2.1 Concentration effect. Reflectance of all PVP samples was computed by using equation 2. The results of reflectance were plotted in the figure 4. It shows to have the same behavior of the refractive index, because reflectance equation has only one variable parameter. It's clear from figure below the values of reflectance are increases with increasing concentration. The reason for this is due to the increased number of polymer molecules in solution and therefore increase the density of the solution as the reflectiveness is entirely dependent on the density 24. 2.2 Temperature effect. Figure 5 illustrates the dependence of reflectivity on temperatures investigated with selected 3.0% PVP of 3 systems. It indicates that at the fixed concentration, the refractive index decrease linearly with the temperatures 25, 450C, and this is because that the increasing of the temperature leads to decrease in the particles of solution in the volume unit and decrease the density of the solution 26, 28. 2.3 Molecular weight effect. The effect of molecular weight on the reflectivity for each system was plotted against molecular weight for selected 3 concentrations, 0.3, 1.0, and 5.0%, and selected temperature 350C as an example. This is demonstrated in figure 6. It can be seen from this figure that the increasing of the molecular weight shows rather rapid increase in the reflectivity solution with molecular weight. This general increase of reflectivity with molecular weight may be due to the increase of polar side groups in the molecular chain of this polymer 29. 3 Coefficient of fineness, F. The fineness coefficient is defined as a measure of the severity of interference fringes and measured for the prepared samples by using the equation 3.30, and the coefficients of fineness values were obtained for all studied systems. 3.1 Concentration effect. The curves between the fineness coefficient against concentration for 3 systems in its selected 350C as an example, have been plotted in figure 7. This figure shows that the coefficient of fineness of all PVP samples have the same behavior to their reflectance, because this coefficient depends on reflectance. From another aspect the influences of addition lead to increase the values of fineness coefficient. This is because the increasing of reflected light is a result of increasing the density and this results agreement with reference 30. 3.2 Temperature effect. The coefficient of fine was also plotted against the temperature of 3% PVP in chloroform solutions as an example, for 3 different molecular weights, which shown in figure 8. It is obvious that the decrease of coefficient of fine with increasing the temperature is because the increase in temperature leads to a decrease in the particles of solution in the volume unit and decrease the density of the solution with increasing temperature 31. 3.3 Molecular weight effect. The coefficient of fine's dependence on the molecular weight of the PVP in chloroform solution, for 3 selected concentrations, 0.3, 1.0, and 5.0%, and selected temperature 350C, as an example, which shown in figure 9. It has been seen that increasing molecular weight shows rather rapid increase in the coefficient of fines of solution. This general increase of coefficient of fines with molecular weight may be due to the increase of polar side groups in the molecular chain of this polymer. 4. Critical angle, C. The critical angle is defined as the angle of incidence for which the angle of refraction is 90 and then reflected light fully reflection or internal reflection. The critical angle is calculated using equation 4, 24, 25, for all the studied systems, where n is the refractive index of the solution. 4.1 Concentration effect. The critical angle values decrease linearly with the increase of the concentration for 3 different molecular weights and at a selected 350C as an example, as shown in figure 10, because it is inversely proportional of their refractive index, or it is clear that as concentration increase, the density also increase and causes critical angle to decrease, and this is agreement with 25. 4.2 Temperature effect. The critical angle were also plotted against temperature of PVP in chloroform solutions for 3 selected concentrations, 0.3, 3.0, and 5%, as an example for 3 different molecular weights, where it is found in figures 11, which is shown the increase of the critical angle with the increase of the temperature due to the inverse relation between temperature and refractive index 32. 4.3 Molecular weight effect. The critical angle dependence on the molecular weight of the PVP in chloroform solutions, for 3 selected concentrations, 0.3, 1.0, and 5.0%, at selected temperature 350C as an example, is demonstrated in figure 12. It can be seen that increasing the molecular weight shows rather rapid decrease in the critical angle of solution. For conclusion, the optical properties of PVP in chloroform solutions for 3 molecular weights, 25K, 44K, and 700K, with different solutions concentration and with temperature range from 25 to 45 degrees Celsius, have been investigated. These polymer solutions show a continuous change in their optical properties as a result of concentration increasing of PVP, which led to development of these properties. Also, the increasing concentration of PVP leads to increase in the refractive index and the reflectivity of the solution, thus it can be used to protect the human skin from the sun's rays and for the production of sunglasses so that the human eye can be protected from the risk of these rays. Credit authorship contribution statement. Marwa. S. Alhosh, conceptualization, methodology, and writing, original draft, Zainab Ettarhouni, methodology. Laila M. Abusen, methodology and writing, review and editing. Abdulhakim A. Jangher, conceptualization, methodology, writing, original draft and writing, review and editing.